Welcome to episode 2 of the Do-It-Yourself 8-Bit Computer video series. Today I'm going to talk about basic electronics. And this is certainly not going to be a comprehensive treatment of electronics and electronics theory and how to use arbitrary electronic components and build arbitrary circuits. I'm just going to try to focus on fundamental skills and give you just enough of a start that you can follow along with future videos in the series and get started on some experiments with digital electronics and the material that's going to be coming in subsequent videos. And in particular, I'm going to focus on the skills that I think are truly fundamental, in the sense that if you have them, then I think you're in pretty good shape to do quite a bit. And certainly you'll be in good shape for following along with future videos. And those are specifically being able to read a schematic of a circuit, and also being able to build and test a circuit on a breadboard. And a lot of what I know about electronics, really is as much through experimentation and trying things as it is from, being absolutely knowledgeable about the theory of electronic circuits. I will cover a little bit of theory just from my own perspective, but what I think you will find is that for the type of electronics we're going to do in this video series, you don't need to know a ton about circuit theory. Okay, so to follow along with what we're going to do in this video, you will need a few things. You will need a solderless breadboard. You will need to have some kind of 5-volt power supply. I'm going to give you a recommendation for a really easy and inexpensive option. If you have a bench power supply, that's great. You don't actually need one. It's easy to find switching power supplies that will work just great for this kind of application. You will need some jumper wires in order to make connections on the breadboard, and then in terms of components, you will need an LED, a resistor, and a push button switch. We're just going to build a really simple circuit to light an LED when a button is pressed. Okay, let's move on. Okay, so what I think the fundamental idea of electronics is pretty simple. That when you have in an electronic circuit, you have a higher voltage at one point in the circuit and a lower voltage at another point in the circuit. Electric current wants to flow from the higher voltage to the lower voltage. And the greater the difference between the voltages, the more energy there is per unit of charge, and thus the more power can be dissipated or used as that current flows. And when you have current flowing through certain types of devices like LEDs or even things like motors, that moving charge can do useful work, like lighting up the LED. So here in my little diagram here, here is a device that is producing different voltages, specifically a battery. So on one side of the battery, there is a higher voltage. On the other side of the battery, there is a lower voltage. And thus, because there are different voltages at these 2 points in the circuit, and because we have created a conductive path, with these wires, current will want to flow, through the wire, and then along the way it may light up this LED by flowing through the LED, and then it will flow towards the negative voltage. So that's just sort of the fundamental idea, is current wants to flow from a higher voltage to a lower voltage. It is worth noting that it is possible to do useful things with voltages without necessarily having current flowing, and we'll definitely see that with digital circuits, where in many cases, especially for something like an input of a digital logic IC, that it is sufficient simply to hold that input at a certain voltage, a higher voltage or a lower voltage, in order to control the behavior of that component. And that can be useful even if little or no current is actually flowing. Simply the application of the voltage is sufficient to control that component. So next, let's talk about Ohm's law. Ohm's law is going to relate three important properties: voltage, which we've talked about, current, which we've talked a little bit about, and resistance, which we haven't talked about yet. Resistance is essentially the tendency of a segment of a circuit or a path between two different voltages. It's the tendency to resist the flow of current. So essentially, when you have resistance, you get less current. So Ohm's law is quite straightforward. The voltage is going to be equal to the current times the resistance. Now, if you consider a circuit that is powered by a constant voltage, and your typical power supplies, things like batteries, wall wart, switching power supplies, tend to produce a constant voltage. So it will produce a lower voltage and then a higher voltage, where the higher voltage is a fixed number of volts above the lower voltage. So when we have a constant voltage, Ohm's law implies two things. First is that when we have a low resistance, it means we're going to have a high current. So the lower this value R is, the higher this value I, which is the current, is going to be. And correspondingly, a high resistance is going to imply a low current, so that if we have a high value of R, we are going to get a lower value of I, the current. And this leads to one very important consideration, which is that the conductors in the circuit that we use to create a path for current to flow in, meaning specifically wires, conductors have a low resistance. So if you have a low resistance path from a higher voltage to a lower voltage, you're going to get what's called a short circuit. So here's an example. If we have a battery, the battery is producing a higher voltage and a lower voltage, and here we've connected a wire from the positive terminal of the battery to the negative terminal of the battery. Because this wire is going to have a low resistance, a very high amount of current is going to flow through this wire. This is a pretty big problem. Short circuits are not good. So among other reasons, when conductors have a high current flowing through them, they tend to heat up. So this wire could get very hot. It could burn. It could cause things to catch on fire. Batteries can wind up getting very hot, overheating, potentially explode when a high amount of current is sort of flowing out of one terminal and into the other terminal. Neither of these is desirable. So one thing you should always keep in mind in any circuit is that you want to have some reasonable amount of resistance between any higher voltage and a lower voltage. And that is where resistors come into play. So resistors are a common circuit component, and what they are useful for is limiting current. And this is completely just an application of Ohm's law. By choosing the correct value resistor, we can control how much current is flowing through a particular part of the circuit. And we're going to see that in our example circuit in just a moment. Okay, so here is our example circuit right here. This is a schematic. A schematic is essentially a blueprint for a circuit. It tells us what components exist in the circuit. It also tells us how the components are connected to each other. In this particular circuit, we have a voltage source, a push-button switch, a resistor, and a light-emitting diode. And you can see that each of these components is represented by a schematic symbol. And one of the skills you will develop as you work with electronics is the ability to read a schematic, and then based on the symbols that stand in for the components that are part of the circuit, you will know what the components are. So I've drawn a little picture of each actual component as it may actually appear sort of physically. So resistors, if you have a sort of a standard through-hole resistor, these tend to be kind of these like cylindrical things that have two wire leads sticking out. That's what resistors look like. Here is my little drawing of a light emitting diode. There is a plastic dome. Usually there's usually it's diffused to kind of diffuse the light that's being produced by the LED chip, which is sort of internal to it. And then there are two wire leads. One thing you will note about LEDs is that the leads are different length. The longer lead is the anode, and one important property of all diodes, and light-emitting diodes in particular, is that current can only flow through them in one direction. And in fact, the little triangle thing here, you can think of that as being an arrow that indicates current can only flow through in the right direction. So, meaning if we want the LED to light up, we need to apply a higher voltage here and a lower voltage here, higher voltage at the anode and a lower voltage at the cathode. And then finally, this is the schematic symbol for push button switch. You can kind of imagine kind of pressing down on this thing, having it create an electrical connection between these two contacts. They're all different kinds of switches. The kind of switch I'm going to show you in a moment is basically this sort of cylindrical housing with a plunger, and you press down the plunger, and that internally, applies a piece of metal that creates a connection between the two leads. There are these little metal tabs that when the plunger is pressed down, current can flow into the one lead and out of the other lead. So hopefully this makes a little bit of sense, that you can kind of get a sense of how this schematic shows how these different kinds of components are connected. One very fundamental notion with schematics, and again, this is something that is part of, it's one of the essential skills that you will need to learn in order to work with electronics, is when there is a line drawn between two components, it means that they are connected electrically to each other. Via some kind of conductor. So you can imagine that this is a wire. Maybe these are actually, physically attached to each other. But in general, the existence of this line, this wire between the two components, indicates an electrical connection. So when an electrical connection exists between, two components, or more specifically, two pins or leads of two components. And remember, in the case of this LED, there are these two different leads, and they are not equivalent to each other. This is the anode, this is the cathode. Here we are implying, or what the schematic is implying, is that the lower voltage output from the voltage source is connected to the cathode of the LED. They are electrically connected to each other. When two component leads are connected electrically to each other, we describe them as forming a node in the circuit. And a node in the circuit, or a node in a circuit in general, simply means that this is, one or more component leads or pins or connections that are all electrically connected to each other. And there's also a node here between the positive output of the voltage source and one side of the switch, one terminal of the switch. There is a node consisting of the other terminal of the switch and one lead of the resistor, and then finally there's another node consisting of the other lead of the resistor and the anode of the LED. So there are 1, 2, 3, 4 nodes in this circuit. All right, so we have one very important unknown in this circuit, which is what value do we need for this resistor? So let's make two assumptions about this light-emitting diode. We're going to assume that the forward voltage of the diode is 1.9 volts. We're also going to assume that the maximum current that we can allow through this LED is going to be 20 milliamps. And in general, any light-emitting diode, if you try to push too much current through it, it will burn out and stop working. Thus, that is the role of this resistor. This is a current-limiting resistor to make sure we don't have too much current flowing through the LED. Okay, so what exactly does forward voltage mean? So essentially, any diode will have a forward voltage, which means that the voltage that we measure at the anode will be a certain amount different than the voltage that we measure at the cathode. And so 1.9 volts is pretty typical for a standard efficiency LED. So what does that mean for the value of this current limiting resistor? So the idea is we are entitled to look at this node in the circuit and just kind of arbitrarily say, we're going to consider this node in the circuit as being 0 volts, specifically this node that is attached to the negative or low output of the voltage source. So knowing that we have a forward voltage of 1.9 volts, that should indicate that this node in the circuit at the anode of the LED, that's going to be 1.9 volts. Okay, now assuming that our voltage source is 5 volts, meaning that we are producing 5 volts at this point in the circuit, that means that we have 5 here, we have 1.9 here. Well, and we're going to have 5 here when the switch is closed. That then creates a voltage difference across this resistor of 5 volts minus 1.9 volts, which is 3.1 volts. So essentially we know there's going to be 3.1 volts across this resistor. Knowing that, we can now apply Ohm's law to determine what resistor value is necessary to limit the current through the resistor and thus through the diode to 20 milliamps. And so the idea is that because the resistor is in series with the LED, whatever current is flowing through the resistor, by definition, is also flowing through the LED. All right, so Ohm's law tells us that voltage is current times resistance. Well, the 3.1 volts across that resistor is equal to 20 milliamps, or in other words, 0.02 amps, times the resistance of the resistor. Well, doing a little algebra, if we divide 3.1 divided by 0.02, we find that the resistor value is 155. So in other words, if we have a 155 ohm resistor here, that will limit the current through the LED to at most 20 milliamps. One thing you will in general find with LEDs and current limiting resistors is that it's fine to use any resistor value as long as it is larger than the sort of the minimum required to ensure that you don't exceed the maximum current. So I would look at this and say, well, technically this says that we should use a 155 ohm resistor. I might choose a 200 ohm resistor or a 220 ohm resistor. Either of those would be perfectly fine in this case. Okay, well, I said at the beginning of the video that I would show you a cheap way that you could power circuits using 5 volts. So the solution is find one of these 5-volt switching power supplies. And there are just a huge number of common household devices that use this type of power supply. So for example, if you've ever had like a USB hub or a router, it has probably used this type of power supply. So just find one of these. It should have a a barrel jack connector at the end of it. That is a really nice way of powering circuits that require 5 volts. All right, let me show you this in a little bit more detail. All right, so here's a close-up on this power supply. I apologize for the somewhat poor lighting, but the relevant details you can see here are it is 5 volt, 1.5 amps. That is plenty for just about any circuit, simple digital circuit, microcomputer circuit, the kind of thing we're going to be building in this video series. Totally adequate for those types of circuits. So if you can find something that has these specs, 5 volts and at least 1 amp, more is better, but 1 is plenty, 1.5 is plenty. Find something like this, you should be good to power your circuit. So once you have found a little 5-volt switching power supply like this one, the next question is, how do you get your actual power supply voltages that are appearing on this barrel jack connector? How do you get those onto your breadboard? And what you really want is to get these power supply voltages out onto wires. So a nice approach is to use one of these little connectors. I got this one on Amazon. Basically what it is it is a barrel jack, a female barrel jack connector on one side, and then screw terminals on the other side. So you can basically plug wires into it, tighten down these screws to the wires. Now your power supply voltages are appearing on those wires. Plug the wires into your breadboard. You are now good to power your circuit. So let's give this thing a try. Okay, so I have my switching power supply plugged in, and I have the screw terminal adapter plugged into the barrel jack. And so now I want to make sure that I know of these two terminals on the adapter, which one is the lower voltage and which one is the higher voltage. It's actually marked. It's marked this one being negative and this one being positive, so presumably lower and higher. I'm not going to take it for granted that that's accurate. You do sometimes get switching power supplies that have the polarity in kind of an unconventional direction, and things might be reversed. So I'm actually going to measure it using the multimeter. So when you do a voltage measurement using a multimeter, this black lead, this is sort of the reference point for the measurement. And then the red lead here is going to measure the difference with respect to the reference. So I'm putting the black I'm putting the black probe onto the negative terminal and the red probe onto the positive terminal. Okay, and this is good. So the multimeter is reading positive 5.2 volts, meaning that the red probe is measuring a voltage 5.2 volts higher than the black probe. So it looks like the polarity markings on the adapter are in fact correct, and it also looks like the switching power supply is producing 5.2 volts, which is, perfectly fine for a 5-volt supply. All right, let's talk about solderless breadboards. So this is the easiest and best way to build circuits in order to test them and see if they work correctly. So this is what we'll be using throughout this video series to build circuits on. And the basic idea of how solderless breadboard works is that there are all these little holes in them, and we will plug component leads, so the pieces of wire that connect to components such as resistors and LEDs, we'll plug those into the holes, and that will allow us to create electrical connections between our components. So the basic idea is that there are going to be these groups of holes, and for most solderless breadboards, they are groups of 5, and all of those holes are electrically connected together. And if we plug two component leads into the same group, we will create an electrical connection between them, meaning that we will make them part of the same node in the circuit. So that is fundamentally how we connect components together, is by plugging their leads into these groups of 5 holes. We can, of course, also use wires to connect one group of holes to another group of holes. And again, if we do that, we are effectively making those two groups part of the same node. We also have in most solderless breadboards power buses, and essentially a power bus is typically at the top and bottom of the breadboard these horizontal rows of holes, all of which are connected together electrically, and those are useful for distributing power supply voltages. So by convention, the power supply bus that is marked in blue, that is going to be the lower power supply voltage. We will consider that as 0 volts. Sometimes that's referred to as ground. Ground has another sense that's a bit beyond the scope of the discussion, but the important thing to recognize is that this is where we are going to have our lower power supply voltage. And then correspondingly, the power supply bus is marked in red. That is the higher power supply voltage for us, because we are using a 5-volt power supply. That is going to be a place where we can connect to positive 5 volts. Okay, so we are now ready to build the circuit. We have our solderless breadboard. We have our LED. Notice I have bent the longer lead of the LED, that is going to be the anode. Here is our push button switch, and here is our 220 ohm resistor. I've chosen one that's a bit higher than the resistance that we calculated. That's fine. That just means there will be less than the maximum current flowing through this LED. And then, of course, I am going to use jumper wires to connect the terminals of the power supply to the power rails of the solderless breadboard. And you will also note I have used some jumper wires on the breadboard itself to connect the top and bottom low supply rail and the top and bottom high supply rail. I tend to do that. Basically, it's nice because it means you get both of your supply voltages on both the top and the bottom of the breadboard, which is quite convenient. Okay, I will build this and meet you back here. So here is the completed circuit. I have connected jumper wires to the screw terminal adapter, and then they connect to the power supply buses on the breadboard. It is a very important, commonly followed convention to use black for the lower supply voltage and red for the positive supply voltage, and certainly I think it's a good idea to follow that convention. We have this short jumper wire here connecting from the positive power supply bus to one terminal of the switch. The other terminal of the switch connects to one lead of the resistor. The other lead of the resistor connects to the anode of the LED, and then the cathode of the LED connects via this short jumper to the lower power supply rail. And now, if I press the switch, I create an electrical connection, current flows through the resistor and then through the LED, and the LED lights up. So there is a successful circuit. Okay, so that is it for this video. To give you a sense of what we're going to be doing next, definitely looking into digital circuits. And I'm planning to do a video on basic digital electronics and talk about logic families. There will definitely be a video on combinational logic, things like logic gates. There will definitely be a video on sequential logic, including things like flip-flops. And just to sort of give you a head start on a sense of what you might need if you want to actually follow along with some of the things we're going to be doing in these subsequent videos, well, you need some basic prototyping supplies, breadboard, power supply wires, resistors, LEDs, things like that, things like we use today. And then you will need some digital logic ICs, so I would recommend getting ones that are in the 748CT series, and I'll talk about why that will make sense when we talk about logic families. But I would say at a minimum you'll want to have some of the basic logic gate ICs like the 748CT 00, 02, 04, 08, 32. I will include a link in the description that will have much more information about what you might need for subsequent videos. All right, I will see you in the next video.